So it's still a way of like finding area, basically. If you remember 6.1 and we skipped it, this is an easier way to do the stuff that was from 6.1, which is why I said we're skipping it.
Okay.
So for a visual for you, basically we'll be able to approximate using trapezoids now, the area and stuff under the curves. So that's the direction we're headed in. All right, so the trapezoidal rule, I'll tell you what it says.
Stop it. You just hit me with the nerf.
Am I going to have to take those away?
Yeah, probably.
At least you're honest.
You're the most
Why me?
brutally honest person I know, and I love it. Actually,
No, I'm gonna go. Yeah, I was about to say. I'm gonna give it
is
to Kenny.
so brutally honest.
Katie has
Awesome.
no filter, bro. I just love how he's himself every time.
Yep. It's pretty accurate. Sometimes it's bad, but it's fine. Like, you can't save
I
it.
was holding back on the feet. You couldn't say what you really thought.
Sometimes. Well, sometimes I'm like, stop that. And he's usually pretty right about things, which is a little scary, but it's fine. All right, so to approximate the integral from a to b of f of x dx, we use t equals h over 2 times y sub 0 plus 2y sub 1 plus 2y sub 2 plus dot 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 plus 2y sub n minus 1 plus y sub n. So that's your formula that you're going to be using. I would make sure you are aware of that formula. Where the interval a to b is partitioned into n subintervals of equal length. H is equal to b minus a over n, which you also need to know that. Equivalently, t equals LRAM sub n plus RRAM sub n over 2, which that's more from the 6.1 stuff that we didn't do, but just for reference for you. Where LRAM sub n and RRAM sub n are the Riemann sums using the left and right endpoints respectively. For F for the partition. Just something I'm going to add up here. N is the number of subintervals. So what you're going to notice is we have the formula for H, and it'll tell you how many subintervals we're partitioning it into. So it'll say like, either it'll say like n is equal to 8, or it'll say something like partition it into 8 intervals or something like that, and then, you know, you'll use that. So you'll find H, then we replace H in the formula above the t equals up here. And it's being divided by 2, so pretty much every situation you're going to end up with a fraction. It's not typically going to round out to a nice whole number, but it could. And then the y values are the different points of when we break it up. I want to say we might have touched on this a little bit last year at the very end of pre-cal when we did something with some area stuff, but we would have done it a very, very lengthy way, and we'll do it a little bit of a easier way now. Are you hot or cold?
A little warm.
You can turn it down some if you want.
I didn't.
Don't like icebox us out, but
I didn't know how everybody else.
no more polar plunges for me. Okay.
I feel cold showers in the morning and then warm showers at night.
No, not at all. Never. Can't do it. All right, next is Simpson's rule.
The Simpsons?
Not like the yellow guys.
I think he drops it.
For what? Sure.
All right, you're going to notice that this is going to look very similar to the one we just did, but to approximate, the integral from a to b, f of x dx, use, give me 1 second. Kenny's calling me because they're working on our water heater, so. Hello. Hi. Okay. Okay. Right. Yeah, well, considering this is the second time in 2 months that this has happened, and there's some indication that it might have been happening with the other people that lived there, I feel like we probably better just do the whole thing, but. Right. Okay, I need to teach. I'm in the middle of teaching, so can we discuss this later? Thanks. I will let them know. Love you too. Bye. Kenny said to tell y'all to learn something. It's like, he acts like just because he's not at work that I'm not at work. Like, okay. Anyways. Huh?
I'm not capable of working.
Alright, so formula for this one. S is equal to h over 3. So notice there's a difference right there. Times y sub 0 plus 4 times y sub 1 plus 2 times y sub 2 plus 4 times y sub 3 plus dot 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 plus 2 times y sub n minus 2 plus 4 times y sub n minus 1 plus y sub n. Where a to b is partitioned into an even number n of subintervals of equal length, and h is equal to b minus a over n again. So notice the difference here is that it has to be an even number of subintervals. The other one, I'm pretty sure can be used for however many that it is. So, and typically the instructions are going to specify which method you need to use anyway, so you're not really going to have to worry about that, but I think all the problems specify. Yeah. And most of ours are just going to have us do a subinterval, like 4 subintervals, just for, you know. Obviously, the more we have, the more accurate we could expect our answer to be to what it should be. So, let's see. Normally, I stop and do examples here, but there's only like one more note thing, so I'm just going to go ahead and do that so that you have it. But it is in regards to error. For determining error, so this is called error bounds. If T and S represent the approximations to the integral from a to b of f of x dx given by the trapezoidal rule and Simpson's rule, respectively. So obviously, you know what T and S go with at this point. Then the errors E sub T and E sub S satisfy the absolute value of E sub T is less than or equal to b minus a over 12 times h squared m sub f double prime, and the absolute value of E sub S is less than or equal to b minus a over 180 times h to the 4th m sub f to the 4th.
Is that m sub f to the 11?
Double prime.
Oh.
And this is to approximate points, right?
Do what?
Approximate points.
This is for error,
Oh,
to determine the error within the,
That last bit is m sub f to the 4.
yeah, like the 4th derivative is what that's saying.
Okay.
Like the double prime, we just don't do a quadruple prime, we just write to the 4th.
That's not reading that either.
What?
I don't know, it's not yours.
Oh, shush.
It's just the stronger
Let's see. Let's look at, just for a minute, I'll see if, I don't know if we'll get through it or not, but we'll try. Use the trapezoidal rule. I'm just going to say TR for trapezoidal rule to not have to write it out every time. With n is equal to 4 to estimate the integral from 1 to 2 of x squared dx. And then they'll tell you to compare with the NINT for this, but we'll potentially look at that in a little bit, or like later, but not right now. So first we're going to partition the interval 1 to 2 into 4 subintervals. And obviously they're going to be of equal length, so we're going to use that formula, the b minus a over 2, right? Nope, over h. What? N.
Over n.
I was like, that n up there looks like an h, so I was confused. Okay, so we're going to start with that. So h is equal to 2 minus 1 over 4. So that's going to be 1/4. Then what we're going to do is we are going to evaluate. So that's like step 1. Step 2, we're going to evaluate y equals x squared at each partition point. So I think last year when we did this, like briefly, we made like a table to do all of this. And then we just like added everything up at the end.
Yeah.
But this way, it will actually end up being a little faster to do it this way. Evaluate y equals x squared at each partition point. So you're not just plugging in 1/4, right? 1/4 is the partition between 1 and 2. So it's going to be like 1 to 1 1/4. 1 1/4 to 1 1/2. 1 1/2 to 1 3/4, 1 3/4 to 2. Okay, those are going to be the partitioned intervals that we're looking at. And so maybe I need to write that so we can see that. So we're going from, because again, we're from 1 to 2, so this is going to be from 1 to 1 1/4, from 1 1/4 to 1 1/2. And normally I probably wouldn't write all these out, but just for you to see it. 1 1/2 to 1 3/4. And from 1 3/4 to 2. Now, what I'm going to tell you is, a lot of times when the book does this, they're going to not make them mixed numbers. They're going to make them improper fractions, which are going to be easier to probably deal with. That's probably what we're going to do. They also, like how I reduced this from 1 2/4 to 1 1/2, they're typically not going to reduce them because the goal is to end up with a common denominator.
Oh.
So just be aware of that. It doesn't matter. You just would have to end up getting a common denominator later if you do that. So we are going to evaluate, okay, at each of these points. So y of, I'm going to do it this way. So this would be 5 over 4. So 5 over 4 squared. And it's at like the right end point of it. So for each one, it'll be there is where it's happening. Now, the first one is obviously well, we'll get there in a second. Let's just go one step at a time. Disregard this last one. I'll tell you why in a second. So these three numbers here, we're going to evaluate y of each of those numbers. So 5 over 4 squared is what? 25 over 16. I'm going to go back to this one and call this instead 2 over 4 for the sake of getting a common denominator. Okay? So y of 6 over 4 would be 6 over 4 squared. And what is that? 36 over 16. And then y of 7 over 4.
I'll just simplify it.
I'm not going to because of the common denominator thing. 7 over 4 squared is what? 49 over 16. Then we would just plug it into the formula. So t is equal to h over 2, which h was 1/4. So 1/4 over 2 times the first number, so that's 1. So the two endpoints of our actual interval are just there, and the other ones are 2 times whatever we got. So plus 2 times 25 over 16 plus 2 times 36 over 16 plus 2 times 49 over 16 plus the final endpoint of 2, and then we would be, or well, wait a minute. I need to check on this last number. Hold on. Just leave it there for right now. Because we have to plug it in. Just leave it there. We'll finish this tomorrow. We need to finish something, and I need to explain where this number came from, because this isn't technically just 1 all the time. So we'll pick back up tomorrow since the bell rang.